Let's take a look at one of my favorite functions that we'll ever get to encounter in calculus because it does something really interesting. And you have to understand what's happening to the function because your graphing calculator will actually fail you on this particular function. But we want to look at another case where a limit might not exist. And the reason why a limit might not exist is because of the way that a function oscillates. And so one of the most famous oscillating functions, we know that the sine function has that sine wave bouncing between -1 and 1. So let's consider f of x equal to sine, and I'm going to put something very specific inside the argument of sine. Rather than sine of x, I want to look at the function sine of 1 over x. Now then we know, just because if I look at the 1 over x, I can't substitute 0 in because even though sine is going to be acting on it, I can't have this 1 divided by 0. So f of 0 is undefined. But as we've seen with limits, just because the function's undefined at a value doesn't necessarily mean the limit doesn't exist at that value. Now then, what happens with this function? If you think about what happens with sine, it oscillates between -1 and +1. Well, as x is getting really, really small, again, think of values like 1/10, 1/100th. What happens is this argument inside of the sine continues to grow larger. For example, 1 divided by 1/10 is 10, and so it's sine of 10, and then it's sine of 100, and then sine of 1,000, sine of 10,000, so on and so on and so on. And what happens is, as x approaches 0, this function f of x, because the argument inside of sine is growing larger and larger and larger, what it ends up doing is it ends up oscillating between -1 and +1 faster and faster and faster. And some graphing calculators or graphing apps are better than others at handling this particular function. One of the things I like to use in my classroom is Desmos. I strongly recommend graphing this in Desmos because you can really see what happens with the oscillating behavior. But if you keep zooming in Desmos, you will see where this breaks the graphing calculator Desmos. Some Texas Instrument calculators, they break even sooner than that, and part of it is because the calculator is trying to make sense of what is happening. What basically happens from a graphing standpoint is we come in here, it does bounce back and forth between -1 and 1, and it does it very gradually for a long while. But then as I start getting closer and closer to 0, it has that behavior I mentioned where it starts oscillating faster and faster and faster and faster. And then the same is true from the right side. It oscillates, 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 and it just starts picking up speed and oscillates faster and faster and faster. And the graph looks something like that. It's very, very difficult to draw by hand. And so something very interesting happens. Even though the graph, f of x, it's a bounded function. Remember in our previous video, we looked at functions that shot towards positive or negative infinity. They were unbounded, and that gave us a situation where the limit doesn't exist. This function is absolutely bounded between -1 and +1 for its entire domain, which includes everything except 0. However, because by definition, in order for the limit to exist, we have to be able to say it approaches a singular finite number. So f of x, again, the more you zoom in, the more it just bounces back and forth between -1 and +1. So f of x does not approach a single finite number. And so because we can't definitively say, yes, it's approaching 0, or it's approaching 1, or it's approaching -1, we must say that the limit as x approaches 0 of f of x does not exist. This happens a lot of times with trig functions where this kind of behavior happens. They have an oscillating nature to them. And one of the things that can be very, very deceptive is that these kinds of functions can break a graphing calculator, or you can get a very deceptive graph out of a calculator. And that's something that would happen with this function. Again, it has to approach a single finite number in order for the limit to exist. This one doesn't, and that's why we end up with this statement right here.